Hello, this is Math Kimchi, and in this video, we'll be looking at a convex hull and one of the simple ways to find it. So first of all, what is a convex hull? Uh, well, say we're given a set of points, like shown below, and convex hull would be a convex polygon that contains all of these points, and by convex, I mean the inner angles of the polygon are all less than 180 degrees. So in this specific set of points, our convex polygon would be like this. So we can see that all of the points are inside of this shape, and also the inner angles. So for example, from A to C and C to H, this angle is less than 180, and this is less than 180. And if, for example, it went from A, C, D, and H, then it would not be convex anymore, because this angle from C, D, and DH in this way would not be less than 180 degrees. Um, and so that's what a convex hull is, and it's sounds pretty simple, but uh, it is kind of tricky to implement this in a computer. So one of the ways I thought of this when I one of the ways I thought of to solve this is by having a circle or some other shape that initially completely surrounds this shape, or all of the points, and that might look something like this, and uh, this. And basically, the idea was that slowly the radius of the circle would kind of shrink until you got to a collision like E, and then somehow this wouldn't really be a circle anymore, but it would be like a squished oval, and then it would kind of like intersect with C and A and H and G, and uh, when it intersected with A, C, H, G, and A, then the shape would look like this, uh, and then it could no longer be smaller without uh, not being convex, uh, and oops, uh, yeah, and basically the Jarvis the Jarvis March is a similar way of doing it, but rather than thinking about it like a rubber band, it's more like you start from one edge and you kind of start getting narrower by kind of putting a tape on G and kind of rolling the roll of tape until you get back to G. Or another way of thinking about it is by rolling this entire set of points on the ground, or a more mathematical way of thinking about it is finding a point on the edge and having a line that kind of has it so that one side of that line contains all the points and the other side doesn't, and you rotate that line until you get to intersection. So that would be E. And now there's a new line, and it's like this. And you rotate on even further. And now A becomes the next pivot, and then C will become the next pivot. And then, yeah, when C is the pivot, it'll go to H, and then again to G. And that's the idea behind Jarvis March, and I implemented it in Python. So let's kind of analyze the code that I wrote. So this is the function. It's like the main function, and first of all, it takes in a list of points, and in this case, points is just represented as another array, and the pivot is the point with the smallest y value, so that's going to be the bottom point. And there's also angle, which starts at 0, and hull starts out, the convex hull starts out as just the pivot, but it's a list. And now we have a while loop, and you look at the next point, and you say pivot becomes the next pivot, and I guess you can print the pivot, and if pivot is less than, so if the new pivot is equal to the very first pivot, then that means that we went a full circle, I guess, and came back to, for example, G. And so we can just return the hull. Otherwise, we can add a pivot to the hull, and then reset the angle. And the angle is between the previous pivot and the new pivot. And so let's look at angle finder. So this is so this is the original point, so in our case the pivot, and this is just any other random point, and this is the change in x and change in y. So I guess you can say this is rise and this is run. And if x and y are both 0, then you basically return anything bigger than 2 pi, I'm pretty sure, but I just went with 9001, I guess, to be safe. And if x is 0 and y is not equal to 0, then you just return 0. And oh wait, no, this is when the 2 points are exactly the same. So when they're exactly the same, I'm just returning absurd number, absurdly huge number, because all we care about is the minimum angle. So this is just going to be ignored unless this is the only, like all of them are the identical point, in which case, well, that would be pretty bad. And otherwise, you say that if x is equal to 0, return 0. So that would be like, in this case, the angle between these two are 0. So that's all that's returned. And this basically returns the angle using the arctangent, and all of these if else statements are just for each possible quadrant. So well, y over x is what tangent is going to be, so arctangent of y over x is going to return the angle, but we also have to remember that arctangent isn't for all four quadrants, and yeah, arctangent only works for the first and the fourth quadrant, but the reason why Q4 isn't just math.arctangent is because this is going to be negative, so we're adding a whole full turn to make it positive. And I think we could have done mod as well, but it's fine. And these two, we just add pi to turn it from quadrant 1 to quadrant 2, or quadrant 4 to quadrant 3, I think. And yeah, so that's angle finder. And next point takes in a pivot, angle, and points. So this is the current pivot, and this is, I guess, the previous angle, and points is just the list of every single point, including the ones we've already used. And you basically, it returns points it returns the point, and the point that it returns is based off of this lambda function. And yeah, this takes in counterclock change. So let's see that. Counterclock change takes in the original and u, and it just calculates the amount that is turned. So for example, from this point, if that was original and I don't know, this was new, I guess. Yeah, and let's just have a horizontal line. And alright, so if this to this, like this was original and this to this was new, then, well, this one doesn't really make sense, or I guess it does. So let's say our current pivot is E, and we're looking at this line versus this line, then this will be the current angle, and I guess we can say this is the what did I call it, new angle, then what it would return is this angle, how much we turn to the left. And the reason why we can't do simple subtraction is because uh, if we have it so that we're going from, for example, here to here, then we'd have to return this and not just this. And yeah, if we return this, then it would be a negative number, which would throw off everything. And yeah, for this I also could have written just modulus, but yeah, a lot of this code could be better, but yeah, I wrote it quite a long ago, so yeah. But anyways, that is how counterclock change works. And next point just finds whatever has the smallest counterclock change, and it finds the new point to minimize the degree angle changed, and then it returns the point. And with that point, we go on to set that to the new pivot and do everything we discussed earlier. So let's just see if this works. All right, so it's saying that the convex hull is this. So let's see. Let's first of all get rid of all of these. Right. And I guess we can leave up the polygon. That's weird. Right, we have to get rid of this because I think I shifted it on accident. And 60. $40 and 0 and 30 and 70, 30. I think they should be 50, 10. Yep. And 20, 10. Alright, and let's see what this says it is. So 20, 50, 10, 70, 30, 30, 60, and 0, 30. So let's see if that's right or wrong. 20, comma 0 is wait. Oh, they should be 20, 0 and right. this changes the general shape, but it still works. So let's see, 2010. So this is the first point, and then the next point, 5010. So that's this one. Right, so far so good. Next one should be E, which is 7030, right? And it says 3060 is the next one. And yep. And the next one should finally be 030. And yeah, so that's a pretty cool way of finding a pretty cool shape. And that was the Jarvis March algorithm, and that one is basically n squared in the worst case scenario, because there can be n total pivots, and for every pivot you have to kind of go through every single possible point, or I guess you could take out a pivot every time you use it, and that would make it slightly better, but it would still be a n squared algorithm. And the fastest one is called the Graham scan, and that one is an astonishing n log n, and the way it does it is very cool, and maybe I'll make a video on it next time. But for now, thank you for watching, and goodbye.